Welcome to the Earth Science Classroom. Today looking at the outer core, and in particular the electromagnetic field that is generated in the outer core. And we're going to look at first the review of the composition of the outer core, what it's made of, the depth, and the kind of sheer size we're talking about in terms of a interior layer of the Earth. We're going to look at the molten liquid material that is flowing throughout this outer core and around the inner core, which is solid. And we're going to look at the electromagnetic field, which is generated from this movement and how it is, and a little bit of basics into magnetism and electricity. So a quick review from previous videos. The inner core is going to be solid, or is solid, due to the pressure, and it's basically solid chunk of iron and a little bit of nickel. Okay, so it's metallic. It is very heavy, very dense, and the outer core right here is liquid or molten. The rock is in a molten state. It has passed the liquidus line, so therefore the temperature is basically higher or greater than the pressure, even though the pressure and density is insane. That temperature is higher, so it allows for the rock to become molten, and this is due to the composition. So we have, iron again in there. We have nickel. We have some trace elements of oxygen, trace elements of potassium. And we also have the sulfur. The sulfur is around 12-15% sulfur, which allows the melting temperature of this area to decrease. Therefore, it makes it easier to melt this outer core. And with the insane amount of heat being generated in this core through two main reasons. So heat is generated inside the Earth and mostly inside of the core and the Earth through one, radioactive decay. So decay of uranium and thorium and radon and also potassium as well. So we have these various elements that are unstable isotopes, which break down over time, alpha and beta decay, and that releases a lot of heat, and that is one of the main things that heats the inside of the Earth. And this has been happening since the start of the Earth's life cycle, lifespan of 4.6 billion years. And the other heat is primordial heat from friction and collisions when the Earth was basically increasing its mass through different collisions and accretion, basically, at the early stages of the planetary lifespan. So the heat that is generated comes out and flows through. So we have obviously conduction, where the outer core is touching the inner core, and there is a transfer of heat energy, thermal energy, and also we have convection. The two main ways or methods that heat is transported within the inner core and outer core, and obviously out into the lower mantle, which we know is the mesosphere. So imagine the outer core as a place that is superheated between the depths of 2,900 to 5,100 kilometers at temperatures of between 2,500 degrees Celsius up to a maximum of like 5,000 or above. So this is way beyond all of the known minerals melting points. So in theory, everything should be liquid, but also you have the pressure, which is insane. So the PSI goes from basically 19 million PSI down to a possible, 39 to 42 million PSI. So the insane pressure, but presence of sulfur allows it to melt and become molten. Now it is moving. Now, this is very, very important to remember and keep in mind all through this video is the movement. This outer core, this molten, millions and millions of tons of molten iron and nickel at 2, 3, 4,000 degrees Celsius is basically slowly but surely circulating around the inner core, underneath the lower mantle, circulating this very hot, it's very what we call turbulent convection. All right, so this pretty much is the basics of the composition and depth and characteristics and the fact that it's moving. And we're going to look more at how this region of the Earth's interior creates the electromagnetic field. So first, let's build the basics. Then we'll get on to the second video. The composition. Let's take iron and nickel. So iron is right here. Now, why is it called Fe? Well, the Latin origin of the word iron, or Latin derivative, is ferrum. And any iron is the most common, most popular, most well-known naturally magnetic element. So we'll get onto what that means later, but it's cultures, countries, people have known about iron being naturally magnetic for thousands of years and being useful in human society for different applications, jobs. And iron is basically, it melts at 1530 degrees Celsius. So as you can see, the outer core is above that melting temperature. So basically, iron is able to melt and become molten at this depth and temperature. However, another one, the Curie point, which is the temperature at which these elements lose their magnetism, lose their naturally characteristic magnetism. So they lose magnetism at this temperature. And for iron, it's 770 degrees Celsius. So anything above that, so if iron gets to a temperature of, let's say, 780, then it will be not as magnetic. It would lose some of its magnetic properties compared to iron that is at a colder temperature. So this is very important to discuss because as we've shown, the outer core is a lot hotter than this Curie point. Yet iron is the main element that's in the outer core, and that's what drives this electromagnetic field. So it's electrical current and magnetism. So how does this element maintain its magnetic properties at the higher temperatures? Well, comes back to this blue term right here, turbulent convection. The fact that the outer core is moving creates what's called a self-sustaining geodynamo. And dynamo is movement, and geo is the earth. And self-sustaining means that there's no exterior or external help. It's an engine, so to speak, that keeps on running without any help or external influence. So the earth has its own engine that doesn't stop, that is heated from decay and friction and accretion, that is constantly moving through convection, and also you can add in there the Coriolis force, the spin of the earth, plus the convection, creates this turbulent movement within this large molten area, and it allows the Earth to make this electromagnetic field, or what we call the EM field. So the next video in the series will look at the principles of electrical currents and magnetism, and discuss also what the EM field is, how it serves us as a planet and also as humans on this planet, and we'll look at the applications as well.